Welcome to the 9th chapter on reactions and delays in the logical foundations of cyber-physical systems textbook, where we will be studying time-triggered control systems as another very important control paradigm. Event-triggered control that we saw in the previous chapter focus on responding correctly to the appropriate events. Downsides were that they assumed that these events are actually detected perfectly, but that simplifies their design and analysis and makes them slightly hard to implement. In time-triggered control, you focus on reacting to changes within a certain reaction delay. That has the benefit that implementations become quite straightforward, because all you need to do is just repeatedly execute with a certain maximum time period of delay, or run things periodically with at least a certain frequency. But while time-triggered control models are much easier to develop than event-triggered control models, the additional effects of reaction delays complicate the control logic and safety arguments quite considerably. Remember, in the 7th chapter, we've seen how to reason about loops using invariants, and in chapter 8, we studied the important feedback mechanism of event-triggered control, and also used the invariants very centrally for rigorously reasoning about event-triggered control loops. Those invariants led us to develop and discover rather important subtleties with the events that could easily be missed if you do it naively. The final system we designed for the event-triggered control, for the ping-pong ball, remember, that was actually quite clear and systematic, but there were a large number of modeling subtleties along the way, resulting from the high level of abstraction that event-triggered control systems has. They do assume that the events are detected perfectly and right away all the time with continuous sensing assumptions, which are hard to implement. Because when you think about it, in an implementation with a controller, you can read sensor information, probably only every once in a while, actually. Then you can process this sensor information to check whether, for example, your current height is actually less or equal 5 or is approaching 5. But that processing takes a little while, the decision takes a little while, everything only takes a little while and isn't permanently executing, even if it is running very often. And that leads us to the second important paradigm for making cyber and physical systems interact: time-triggered control, where you take periodic actions to change the system behavior only at discrete time points. Now, it doesn't have to be perfectly periodic, like say exactly once a second. The time-triggered control paradigm is just as important and in fact more realistic if you say the system can react a little bit faster or a little bit slower, but it will react only at certain discrete points in time, every once in a while. Both of those control paradigms, event-triggered and time-triggered, are very fundamentally important, and it's important to understand the relationship of both. What we will be learning is a lot of very crucial lessons in modeling and controls of cyber-physical systems in designing their time-triggered control principles. Time-triggered control is pretty easy to implement, but surprisingly subtle to control correctly. In particular, what we'll be learning in modeling and controls is to identify the appropriate feedback control principles and identify the relevant dynamical aspects in cyber systems that come from events and the ones that come from reaction delays, to identify which is the most natural model for something. We'll in particular be focusing on discrete sensing, so sensing at, non-deterministically chosen discrete points in time. On the computational thinking side, we will be using loop invariants to guide our thinking quite centrally, and we'll understand how to design time-period control systems and a very important principle of how to design by invariant. So we will be leveraging the invariants in the design of the system, which is taking us a long way in the correct by construction principles. On the CPS skills side, we will look at the precise semantics of time-period control, which maybe isn't so hard to understand, but it does give us important lessons for the intuition about their operational effects. We'll also learn how to find control constraints, which is absolutely fundamentally important in time-period systems, and we will study certain aspects of higher-level model predictive control principles. Let's understand time-period control. Let's look back at our bouncing ball models and understand the impact that delays have on controls. So here was our verified, provably safe ping-pong ball for the vertically bouncing quantum. So it was starting somewhere between 0 and 5, initially going with velocity less or equal 0, some assumptions about parameters, and then the bouncing ball, which we call quantum, is falling according to these differential equations of lower physics and upper physics, after which an event-triggered controller, which is listening to these events, will take action and correspondingly flip the bouncing ball upwards again if it is on the ground by inverting the velocity. So if it is between 4 and 5, so the event happens at the latest at the point 5, then we take the ping pong paddle and hit the bouncing ball over the head, which will send it back down and up. And for example, here we reacted a bit early, which is fine. It's between 4 and 5. So we hit the ping pong ball over the head with the ping pong paddle and send it down, and so on and so on and so on and so on and so on. So it can bounce pretty quickly, but always within the safe heights is 0 and 5, which is precisely what this property states. And we proved that last time using, crucially, this loop invariant. That's amazing, but when it comes to implementation of it, it's pretty complicated to implement the event detection that we're always below height 5 at maximum reliably, because remember, the semantics of this differential equation with the evolution domain constraint that we're above ground and below height 5 is that always when following this ODE, at every moment in time, do we check that whether we're above ground and below height 5? And that's really complicated. I mean, maybe checking above height 0, that's easy because our physical surroundings are making that happen. If this is a solid surface on the ground, then, well, we don't need to worry about the bouncing ball falling through it. It just can't. But the height 5 up here is solely for the pleasure of our controller. It just says at the height 5 at the latest, do we want to do something about it? But that's ultimately a control's responsibility, not, as down here, a physics responsibility. In other words, the event-triggered model is a beautiful model. It's provably safe. We've done that last time. It isn't even quite so complicated to get right after you get the model okay, but you can't implement it. So the issue is that you have some justifiable events, like, for example, checking for physical events. Are you on the ground? Where you can even use the exact equality comparisons if that's where your ground is at height 0. And you've got these physical evolution domain constraints, like you want to be above ground all the time. They're, non-questionable. But others are harder to justify. The ones that come from the controller's pleasure, basically, to add into the evolution domain constraint that you really would like to be below height 5 all the time. And the point is that unlike the physics that we live in the real world, our controllers won't literally run all the time. Of course, the controller can be very fast, but they still don't really run at literally every point in time, of which there would be uncountably many. Controllers simply cannot send and compute really all the time. And of course, the bottom line lesson is that if you expect the world around you to change for your controller's sake, you may be in for quite a surprise. That first of all means when designing models, we need to pay careful attention to which parts of the model are physically justified and which parts come in for control reasons, so that we need to scrutinize whether we got them right and whether we can ultimately implement them correctly. So let's just go back to the drawing desk. Here is the original quantum, the ping-pong ball model, which we conjectured to be safe, but it really isn't, because unless we sneak something into the evolution domain constraint of the system, there's no guarantee whatsoever that it will stop early enough in order to make sure that we can listen to the event and use the ping pong paddle to get the bouncing ball be sent back to the ground. Now, we don't want to add in, to make this model safe, some kind of event detection here anymore, because it is hard to permanently sense the position or the velocity of the ball. What else could we be changing in the model to make sure that it is actually a safe one? We're always above the ground and below initial height 5, without adding serious event detection back into the evolution domain constraint models. Well, maybe we could bound the duration of the evolution somehow. Because of course, if we don't do anything, the issue is that we could very well miss the exciting event that the bouncing ball is between 4 and 5. And for example, if we miss that here, the bouncing ball comes way up too high, and we're unsafe at this moment, for example. If we bound the duration of the evolution and say it would only evolve as at the maximum until the time is 1, then I guess that can't happen. Well, hold on a second there. Now, what are we saying? We're saying now that you can follow this differential equation for any amount of time as long as the position is above ground. Well, check. And t is less or equal 1. What's t again? T is just some variable, right? Maybe you meant time, but it didn't say so. T is just some variable less or equal 1 that t apparently isn't changing in this differential equation. Just look at it. X and v are changing. T is not. That means either t is already below 1 initially, which is a matter of luck, but then this evolution domain constraint is always true, so we can follow it as much as we want until we're finally on the ground. And particularly, we could follow it too long here. Or t is initially 20 million, or let's say 5, in which case we cannot satisfy this evolution domain constraint, not even for duration 0. That would all be very bad. Yeah, I get it. I guess we forgot to say that by calling it t, we actually meant time. How can we communicate in our model the fact that we mean t to be some kind of time variable? Well, we add in t prime equals 1 into the differential equation, because that exactly says that t changes as time does with a slope 1. It's a clock that's progressing and its value is increasing exactly as long as we're following the differential equation. So now we got it. Okay, good. So we have a differential equation, t prime equals 1, that says, time is changing, and in addition, simultaneously, while the position and the velocity are changing, and we bound the evolution domain constraint such that we're not just above ground all the time, but also time is at most 1 all the time. So for example, we could be falling here until maybe here the time is 1. Oh geez, and then we need to stop the differential equation, run the control, which, since we're not on the ground, doesn't do anything. Since we're not in between 4 and 5, we don't do anything. So we don't do anything at all, which means we can repeat and wait. We're still at time 1. That's awkward. Next time around, we still can only follow this differential equation for 0 time. It's next time around just for 0. Get it. This has imposed a global limit on the absolute amount of time that we can ever get to. And that's not what we meant to say, right? We wanted to say something about the local duration of this evolution of the differential equation should take at most 1 time unit. How do we fix that? Well, we add in that we reset the value of time to be 0 before we even go into the differential equation. It still evolves with time, t prime equals 1, and we bound it to be at most 1, which means overall we follow each run of this differential equation, each solution, for at most 1 time unit. So for example, here we follow it until we're, say, here, and then we follow it until we're here, and then here, and then here, and so on. Okay, cool. In particular, we kind of sort of wind up the clock here and measure the progress of the duration of the differential equation every time it runs. Yeah, that's a time-triggered system. We're checking our events, but in a time-triggered fashion. After a certain period of time, at maximum 1 time unit, do we run the discrete control again. And we repeatedly do so. So we again run the physics for at most a second, and then run discrete, and physics for at most a second, and then discrete. Spectacular. Is this a safe system? Is it really true that we're always, above 0 and below height 5? Well, there's something very awkward about it. And the problem is that even if we do exercise exactly the right control down here, we literally have no assumption beyond the initial state on what is true in the beginning, which means in the beginning we didn't even run the controller yet. And that's actually kind of annoying, because we would basically have to assume in the initial state that the initial configuration where we're in already satisfies all the constraints that the controller does need for the safety of the system, or we basically need to assume the controller ran at least once before, which is all very awkward. It's a lot more fun to simply swap the 2 lines around and say, first the control runs, and then the physics ODE runs, and then we can possibly repeat this. So control runs and physics runs for at most 1 second, remember? Control runs and physics runs. We simply swap the 2 lines of code around to make it easier for us to analyze and understand, and also make it clear that the first thing ever that runs is the controllers. Good. Now we can ask ourselves, is the system safe? We're listening to the right event. We're listening to whether the height is between 4 and 5, and then we act and use the ping-pong paddle, say up here, and over there, and we could also do that here, but we could also wait until it falls around back to the ground. But are we guaranteed under all circumstances that we're doing this right? No, we're not. And now all of a sudden, even if it is very easy in comparison to implement such a system, all we need to do is make sure this controller is being run at the latest after 1 second again. It is much more complicated to get it safe. Because, even if we're not between height 4 and 5 just yet, there's still the issue that we could be acting much earlier or much later, because the only assumption that we have in the model is that after at most 1 time unit we run the control, which will check for this event, but what happens in between now and the next time the controller runs, we are not being very explicit about, except that the ODE runs. Well, we need to predict a little bit what's happening, because here, for example, say we run after 1 time unit, say here, we run after another time unit, say here, we run after another time unit, say here, and we're already above 5. This is kind of awkward. We'll run again after 1 time unit, but even if we're in the event zone between 4 and 5, where we could be using the ping-pong paddle, we're currently not going upwards but downwards, so we don't actually use it. We maybe listen after 1 second again, and after 1 second again, and maybe now here we're lucky there was 1 second and we exercised the ping-pong paddle right away. But it's already too late, because of course we've been very unsafe up here. So if we're excited to control our system for certain events, we have to take the time delay into account. And there's a big difference between delays versus events. Periodically, even if frequently, monitoring for an event with a certain polling frequency reaction time may still mean that we're missing the exciting events. delays may make controllers miss events. And any discrepancy between an event-triggered controller idea versus a real time-triggered implementation can happen and indicates poor event abstraction. It doesn't always have to happen, right? Sometimes our event abstraction is a good one, but whenever these subtle differences come up, and they matter a lot, then we have to dig deeper and understand the role of delays. And more or less the point is the following, that slow controllers that are monitoring pretty small regions of a fast-moving system usually are in trouble. They have to take delays seriously. But if, for example, you're trying to see whether you moved across an entire football stadium with a lawnmower, you will probably notice whether you're moved somewhere on the football stadium, because the lawnmower is pretty slow and the football stadium is pretty big, so you'll notice this. But when playing ping pong, and now I mean you, responding exactly to the tiny region that your ping pong paddle is at, in a ping pong ball that's moving pretty quickly, you can't ignore the reaction delays. In other words, controllers actually need to be aware of their own delays. They need to know how slowly am I reacting in order to already prepare for the right reaction early, in case they might be missing the next opportunity to do something about it. In other words, we're asking René Descartes and his Cartesian demon again for help before we settle on any agenda of a conjecture that we're trying to prove. We're still skeptical about the truth of all the beliefs until we find a justification for them, which means we found a proof for them, but that means before we settle on an agenda to prove anything at all, we should scrutinize whether we've got all the right assumptions and whether we've got all the right controls and all the right physics model parts. Well, the physics model part was fine and easy this time around, unlike an event-triggered control where the physics model was hard. So, we could miss the event that we're listening for because it happened off control cycle and not during one of the multiples of one time unit, for simplicity, points in time where we're actually running the discrete controller. So what could we do about it? Basically, we need to check not just whether we're presently in the zone where we want to control between 4 and 5, but also whether we could miss the exciting event, whether next time we could already be above 5, right? If we next time the controller runs, we're already above 5, then right now we better do something about it. And how can we find that out? Well, we can solve the ODE. So we can just predict where are we at after one time unit by looking at what's the value going to be like. It's going to be current position plus current velocity minus half gravity. That's where we're at after 1 second, and we can check if that's bigger than 5, then I guess now is a good time to act. And if we rewrite this under the simplifying assumption that gravity is exactly 1, just to make the math easy, then we have half come over to the right-hand side, 5.5. And we've got the velocity coming over to the right-hand side. So we're checking if the current position is bigger than 5.5 minus the current velocity. And if it is, we act right now. So with that, we're checking not just whether currently we would like to act, but we're also checking whether this is the last chance to see. We're checking whether this is the last opportunity where we can act, because after a second, if we're exceeded the bound 5, we should act right now, because a controller, if we're unlucky, will not run again until another entire second has passed. Now the problem is we're checking after one time unit, and we're running the controller again after another time unit, and we're running the controller again after another time unit, and now we're asking ourselves, in 1 second, where will I be at? And well, where will I be at? In one time unit, I'll be here. And that's perfectly safe being here, right? So we're projecting where will I be at 1 second from now, which is below the critical height. So we're not responding yet, but that's kind of stupid because in between we have gone above the safe height. And of course, in this particular execution, you could change it to make sure that, if you have a chance to be running your control anywhere within 4 and 5, you already react. But if we would have just gone faster, we wouldn't have even noticed. And down here, we would have said, in 1 second, we will be safe again because we have already turned around. And notice another small subtlety here. In our event-triggered design, we said we only want to respond with the ping-pong paddle between lower height 4 and upper height 5. And now, in our time-triggered controller, we relax this constraint. We say we use the ping-pong paddle anywhere we want, but we still want to make sure that we never go above height 5. As an exercise, you should think, how do you need to change the vertically bouncing ping-pong ball such that you only use the ping-pong paddle between 4 and 5? Now, what can we do to fix the problem? Not the problem to be between 4 and 5, but the problem that if we check right now where we're at after 1 second, even if that's a safe point, we might have been safe somewhere in between. Well, right here we could check what happens if we insert half a second into the solution, and what happens if we insert 1/4 of a second and 3/4 of a second. So all kinds of these things, but oh boy, these are a whole lot of time units that we need to plug in. And of course, the point is, we cannot possibly put in the uncountably infinitely many points in time that really happen and literally check each and every one of them if we're ever above 5. That's what the proof will have to do for us to make sure that we're always safe no matter what. But our controller can't literally check each of them individually. So we need to do this differently. And what we know still is that as balls keep on flying through the air, we still know the bouncing ball invariance. Just because a bouncing ball has been upgraded to a ping pong ball doesn't make us forget about all of the knowledge we gained when understanding bouncing balls themselves. If we take the ping pong paddle away, the most amazing ping pong ball will still function literally exactly like a bouncing ball does. So while we're not exerting control, I guess this invariant works out that we have understood in lecture 7 about bouncing balls. That 2 times gravity times position is the same as 2 times gravity times initial height minus velocity squared at all the times, and we're above ground at all times, and the things we assume for that, like damping coefficient is 1 for simplicity, and gravity is positive. Let's just simplify this a little bit. And remember, we actually also assumed here that the gravity constant is exactly 1. So I can omit the g's and just write down 2x is 2h minus v squared. And, let's multiply. And let's also remember what was our initial height. Well, we started at 5 at max. So let's just put in the 5. And, when in doubt, we change the initial assumptions a little bit so that the invariant that we have here is very easily 2 times x is 2 times 5 minus v squared, and we're above ground all the time. In other words, this initial height that we're putting in here is kind of like the critical height that we would like to worry about. 5 is still fine, right? But more than that is not. Because more than that, here the critical height that we could ever get to apparently is larger than we would like it to be. So by understanding what happens to our invariant, we can right now already predict how will the ping pong ball be flying as gravity is acting on it. Here, because we're computing what's the critical height by this invariant, we will understand that it could be climbing too high. In fact, it will. Let's use that invariant for design by invariant principle. We just use the invariant to design the control of the system quite crucially, to make sure that if it is ever above this critical height, then the potential energy of the ball exceeds the safe height. So if, as the potential energy is being converted into the kinetic energy, ultimately we would go too high. And that invariant is what we're now using for control purposes by squeezing it in here. As before, we say if after 1 second we're above 5, then we should react right now, but also if we could ever be going above 5, right, by this invariant for critical control. In order to make sure that we're also taking into account the amounts of time that happen in between now and 1 second from now. Okay, so we again ask René Descartes for help whenever there is a proof of this system. And René Descartes helps us understand that it's better for us to simplify the system a little bit and say, let's also assume that we kind of needed to assume the damping coefficient is 1 for these invariants to be the right ones. But let's also assume, just for simplicity, that the ping-pong paddle actually is 1. It's just really just a simplicity assumption. But the problem is that we're not actually safe, because even if this control is doing all kinds of beautiful things, we're only executing it if we're not on the ground. It could happen that we're on the ground and these conditions tell us, well, I would already have to act because 1 second from now I'm unsafe, but we're not even checking these conditions, because if we are on the ground, all we do is make the ping pong ball bounce back from the ground like here and never even run the rest of the control. Which means time-triggered controllers can only help you if they're also running. How do we make sure they run? By change of the hybrid program. All we need to do is identify the culprit. The else was a bad idea. We should be running in every control cycle, not just when we're not on the ground. So we do fix that by turning the else into a semicolon right here. So we first run ground control. Being done with that, we run ping-pong paddle control, which will in particular run regardless of what the ground control decided. Think of this as, using the ping-pong paddle right down here as the ball is being bounced back up. Good. That was a pretty harmless change of the hybrid program. I guess now we're safe and happy. If we ask René Descartes and his Cartesian demon for help, they agree with us. They say, yes, indeed, this conjecture is a valid formula of differential-Lemming logic. It is actually true. Yippee, yay, we've got a safe system. We should relax and walk away and feel very good about it. But not so fast. What could still go wrong? We could have a safe system design that nevertheless is broken because it doesn't allow enough behaviors. We could have broken physics. Well, we didn't break physics really this time around, because the ODE model is just, interrupted after at latest 1 second and let the discrete controller run. That sounds fine. You can still have some existential worries about whether quantum's Münchhausen desire to use ping-pong paddles on itself is acceptable, and you can also worry about, is it fine for quantum to use ping-pong paddles right near the ground? But you can try it out. You can basically put a ping-pong paddle on top of a bouncing ball and it'll do just fine. It'll bounce back. But the problem is that even if we ask René Descartes and his demon for help, who do say, yes, this system is fine, they actually should have said no, because even if the formula is valid, it doesn't allow for particularly long and exciting evolutions, because when we keep on controlling, we're not on the ground in the beginning. This condition isn't true because we're falling, right? So we don't have to do anything. We follow the ODE, let's say until this time unit right here. And then the trouble is we run the controller again. We are on the ground, so we do stuff. After that, we check whether in 1 second, that's not the case, but we do check whether this potential energy is possibly above critical height. And while we are going up, and it is right away here, because it eventually is, right? Eventually, if we would keep on following this, we would be too large, and since this is an invariant, it is invariant. Shocking statement. Invariants are the quantities that do not change the truth value. That, of course, means for us that if it's ever true, then it's also always true. And of course, we ultimately need to act, but not quite yet. Just if we use this arithmetic to check it as an invariant expression, which means it is ever true, it is already true right now, and so right now we would be using the ping pong paddle, and that means there's not a whole lot of exciting bouncing happening in the ping pong ball's execution. It's falling down, and we decide right now, some find in the future, let's say in a million years, will be too high, so let's do something about it right now. That's pretty safe. I mean, René Descartes helped us say yes to this formula, but it's not super exciting for quantum, the ping pong ball, no matter how time triggered it will be. So what do we do to fix this? The point is that this expression tells us if at any moment in time it will be too high up. But we also need to check whether now is the time to act. Back down here, we can still let it fly. Just eventually, we should be acting about it. And basically, when we should be acting is when we're near the turnaround time. Down here, we're still climbing up pretty fast, but up here, we're near turnaround time. And since this is already checking whether we have to act because after 1 second we're in trouble, all that this side needs to do is check that between 0 and 1 time unit, if we go too high, we need to act right now. And that happens whenever the remaining velocity is so small that we're almost turning around already. Of course, we can also predict what velocity is doing then. So we can say the velocity after time t is the current velocity minus gravity times time. Well, gravity was 1, so that's just v minus t. And that means since t is at most 1, this question is that the velocity we'll have after a second will be negative if the current velocity is less than 1. And in fact, if and only if. So the overall condition now says that our discrete controller says if after a second will be above the critical height 5, then now is a good time to act. Or if at any moment during the evolution will we be ever at a height above 5, and now's the time to act because we're nearing this slow turnaround time. Not act right down there yet because we're still happy. Remember, the implicit precedences of the operators tell us that the parentheses have to go like this. We check this or that conjunction. You can think about it on your own. Whether the system would also be safe if I had parenthesized differently here. Let's ask René Descartes again. After all these design changes to the time-triggered ping-pong ball, look, we changed a lot of things in this controller to, approach correctness. But is it actually correct now? Let's scrutinize before we go for a proof. So we ask René Descartes and his Cartesian demon to help, and they do say yes. And now the question is, did they mean it? Yes, they did. This time the model is actually okay. And of course, in order to convince ourselves that the model is actually safe, we should be doing a proof. In order to convince ourselves that the model can move fast enough, it is sufficient if we try it out. And here I did try it out for you. And that's a whole lot of bouncing. That sounds like a lot of fun. Now, how do we prove this proposition that quantum, the time-triggered ping-pong ball, is safely bouncing? That under these assumptions on the initial state, which are pretty harmless, all behavior of this time-triggered control model is such that the ping-pong ball's position is above ground but below height 5. Of course, when we're proving it, we'll first again face the loop. If we're facing the loop, basically the rest of the proof is follow our noses. So again, the most important ingredient in proving this hybrid system is that we need to identify the invariant for it. At this point of the textbook, I'm sure you will no longer just try out the post condition for a loop invariant, because you will already understand that since the position changes with velocity, we also need to know something about the velocity in order to guarantee this. And what we also can remember is that the majority of design of this time-triggered system was by referring back to the bouncing balls invariants that we've identified. I mean, we used them for designing why this control condition was correct. And we used these for efficiency reasons, but never you mind. That means while the ODE is running, the bouncing balls invariants should be holding in these assumptions of everything being one up here. And also, the time-triggered controller is preserving them. So we're using as a loop invariant, of course, the invariants from the bouncing balls, the free-flying phase, where 2 times the position equals 2 times the initial height minus velocity square, and we're above ground. And the only extra thing we need to know is that we're also below height 5, which of course indirectly imposes constraints on these things. And that part certainly does imply this, and this conjunction here links the position and velocity in the appropriate way, in a way that we already saw worked in bouncing ball actions. Oh wait, gee, hold on a second. I mean, capital H, that's this initial height thing. We don't actually have any assumptions about capital H. But that's okay, because all we need to do is add this into an initial assumption, like literally, without even saying that x equals the initial height. We merely say that 2 times x equals 2h minus v squared, which is one legitimate assumption right from the get-go, which indirectly links the position and the velocity of the bouncing ball by way of, essentially, when you think of its entire potential energy combined, taking into account the kinetic energy it already has from the current velocity. And then I guess that means this condition is true in the beginning, which of course means that this conjunction is true in the beginning because the left conjunct we just assumed so, and this conjunction is part of the initial condition. That implies this. And now let's try and understand why this loop invariant actually is a loop invariant. So if it's true before the loop body ran once, it's true again right after. Well, these do not change x, which is a good thing. Nothing ever changes h, but they do change v, so we need to worry about this. These conditions are trivially sustained while the control is running because, well, x isn't changing in the control, only v is. So that's a good thing. That is sort of the thing we need to worry about for the control. For the ODE, what do we need to worry about? Well, if this conjunction is true right after, it's going to be true always after running the ODE as well. Essentially rapid bouncing ball proof, because this was the bouncing ball invariant. And if we knew this, then we also know that. So what happens to the velocity here? Well, if we're on the ground, then the velocity is changing. But remember, the way it is changing is using damping coefficient 1, and that means velocity is being flipped to minus velocity. But wherever you write velocity or minus velocity doesn't matter when you're writing down v squared. And here also, you're flipping around with some wonderful assumptions and things like that, but that only happens with the ping-pong paddle coefficient 1. That means that as v is changing to minus v, again, it's square, doesn't notice. And these haven't changed the value of x, so it is obviously true that they are preserved. So, summarizing, what we've seen today is time-triggered control, which is a common paradigm for designing real controllers, working from periodical or pseudo-periodical control. Pseudo-periodical means that it's not really like exactly 1 second, 1 second, 1 second, 1 second as the delays after the control runs again, because there's a little bit of jitter, like things run a bit slower or a bit faster. The point is, for time-triggered controls to work, we need to assume an upper bound in the reaction delay, because just like in a car, if you have no bound on the amount of time it takes that you can open your eyes again after you just closed them, you shouldn't be driving cars at all. You expect delays, and you expect the inertia in the system to have a chance to control them directly. The plus side is the implementation is pretty easy. All you need to do is get discrete time sensing out working, which is at some non-deterministically chosen points in time, you do check your sensor data. You need to predict events, however. You can't just say, if the event is true right now, then I guess I need to act, but you already need to be preparing yourself for the question, what events could I possibly have missed until the next control cycle, whenever you get to react again. That means safe controllers need to know their own reaction delays and plan accordingly. The burden of the event detection, which is by assumption of the models in event-triggered control, is suddenly brought to the attention of the CPS programmer, which is a good thing because they can no longer fool themselves into believing that systems aren't actually safely implementable or fine. Time-triggered controls are implementable and much more robust, but they do make design and verification considerably more challenging. Which also means that what you may want to do is leverage the knowledge you've gained from verifying an event-triggered model as a basis for designing a time-triggered control model. A different topic that, however, has some interesting lessons for us in store that are typical hybrid systems lessons and does fit to the phenomenon of time is what we will see in Zeno's quantum turtles. Remember how the bouncing ball is bouncing as we change time and plot position over it? Here we understand how quantum the bouncing ball met Achilles and his tortoise in the following way. It's falling in gravity, and when on the ground, we're bouncing back up from the ground by inverting velocity. Beautiful model, we repeat it. We also put a hybrid system spectacle on and zoomed in at this point in time where we understood that at a discrete point in time, the velocity is changing before we keep on flying again. So if we plot time in two coordinates, the real time and the step time, then it's the bouncing ball is falling, and then we change the velocity discretely by negating it, and then we follow the differential equation upwards and downwards for some period of time. And then on the ground, we run the discrete controller which says velocity is being inverted from negative to positive. We again follow the differential equation for some period of time. Then we run the control, since we're on the ground, invert the velocity and follow a differential equation for some period of time, and again, and again, and again, and again. That sounds like a lot of fun. And we can write down the time domain for this as well, where if we just plot the lower plane, then time passes continuously, a jump, and time passes continuously, and a jump, time passes continuously, jump, time continues, jump, continues, jump, continues, jump, continues, jump, and so on. That's great. What's funny about it? If we add up the times, this takes longer than that, which takes longer than that, longer than that, longer than that, for simplicity, let's pretend the first one takes 1 second, and the second evolution takes half a second, and the third evolution takes 1/4 of a second, and then 1/8 of a second, and so on. It's not completely true for the plot I had here, but close enough. Then we add up all those durations, and what do we get? 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. That's the sum from I equals 0 to infinity of all negative powers of 2, so 1/2 power I. We can compute the value of that by geometric series argument. It's 1/1 minus the base point, so it's 1/1 minus 1/2, which, as far as I know, is 2. Great, spectacular. That's funny. If we add up all the continuous amount of time that's ever passing here, it switches a whole lot of time discretely, but it doesn't ever actually, in total, even if it goes to infinity, consume a whole lot of time. At most 2 time units, which is, as far as I know, smaller than infinity. Which means, if you consider a point in time like over here far along, beyond 2, if you add up all those amounts of time here, there will be a limit here, say, that you can never pass. You shall not pass, the Gandalf argument. Which is funny, because that means the point over there realizes it doesn't really exist. It's beyond the total amount of time, too, that the quantum bouncing ball model ever admits would happen. That means the poor point in time realizes this, says it doesn't exist, and vanishes in the logic cloud. That's the pity. The point concludes that it doesn't exist by this logical argument and says, well, then I guess this point in time is never reached. That's sad, though, because if you ever set up a bouncing ball that keeps on bouncing, by this model, it will never make it beyond time 2, which also means that we don't exist. But we do. Every point in time exists. I mean, what this model is exhibiting is that the duration of evolution keeps on shrinking, and this model is violating something that's called divergence of time. This is what is called a Zeno paradox. It's also why it's called a Zeno model. The philosopher who described this was the Greek ancient philosopher Zeno, who said, well, if we have the hero Achilles and a little tortoise, then if they're racing and we put the tortoise here and we put Achilles there, then Achilles, the fast runner, is never able to be faster than the tortoise. Why? Because, of course, Achilles will run real fast. We'll make it to this point. But by the time Achilles is where the tortoise was a moment ago, of course, the tortoise will have gone on. It will be here. Achilles will again run from this position to that one real fast. But after he reaches that position, of course, the tortoise will have gone on. Achilles will run again really fast. And when he reaches that position, turtle isn't there anymore. And so on and so on and so on. In other words, Zeno observed that if you think about the motion in this particular way, seemingly Achilles, the fast runner, will never be able to reach the tortoise. And if you try it out in reality, you'll be shocked to hear that Achilles, the runner, made it all the way here to this point in time, and the tortoise is still, somewhere there at the latest. And so Achilles, of course, can run further until this point, just not by this particular argument. In other words, what is happening here is that this model is partitioning time in a bit of a strange way. That is an important model phenomenon in hybrid systems, in particular, not so much in this physical model where, well, maybe you can understand it by a whole lot of bouncing happening at the end, but you really have to be careful when you're writing down models where your controllers are assumed to be running faster and faster and faster, because chances are they won't quite be able to. Models that are like this, that compute infinitely often in finite time, until time 2, they keep on switching more and more and more often, infinitely often, are not exactly implementable usually. So just these are called xenomodels, and you need to pay some attention when you design systems that are like that.